Okay, so the next group. So which group? There were how many groups didn't go yet? There were 3 that went, and there were 6 total, right? Yeah. Oh, come on. This isn't boding well for the no homework. So, okay, so come on. You were told on Wednesday that the other groups were going to go today, so you should have been prepared. Okay. Yay. I knew I could count on you to save the day.
So our question is the 814. The question is, in what respect is the Luder band formation of the mite stills similar to, and how does it differs from the tensile the behavior of the polymer that draws? So I think the Luder band formation is similar to the neck initiation and propagation of the polymer and the tensile stress. First, both the Luder band formation and the neck negotiation is based on the formation of the plastic flow at the gauge length. And the second, for both the mite stills and the polymers, the stress required to initiate the plastic flow is great. The stress required to initiate the plastic flow usually is greater than the stress required to continue it. And this is the mite stills. This is the Luder band formation. And this is the negotiation of the polymer. And third, for the mite stills, the work hardening comments of the plastic flow has propagated the entire gauge length, which results in a large tensile stress of the polymer. And the strengthening also happens in the polymer after the plastic flow has propagated along the entire gauge length, and which will also result in a significant increase in the flow stress. But the difference is that the work hardening of the mite stills is due to the dislocation. I think it's due to the dislocation interactions. But the strengthening of the polymer is due to the molecular. How to erase it?
Excuse me. The chain alignment, orientation, conformation?
Yeah. Oh, sorry.
Yeah.
The strengthening of polymer is due to the molecular alignment along the neck along the joint neck propagation. And then I think the Luder band strain of the mite stills is limited. This is the Luder band strain for the limited, but for the polymer, the tensile strain associated with the neck propagation is usually very large. And the question 3 is compare the magnitude of the question 3 is compare the ratio of the tensile to the initial yield strength for the two materials. I think the strengthening of the polymer is more effective because after the molecular alignments, the flow stress have to overcome the atomic bonding in the chains. So in this case, the ratio of the tensile to the initial yield strength of the polymer is larger than that of the mild steels.
Okay. So where do Luder's... Oh, what happened? Cancel there. What the heck? I don't want to use OneNote. Faculty don't get a OneNote. We don't get a OneNote account. Only students.
Get a OneNote account?
What? Yeah, quick sketch. All right. So if this is our gauge section, if this is Luder's band and spiel, where is it going to start? Do you know?
You mean which location?
Okay. Yeah, where on there? It's probably not recording. Take a guess.
In the middle.
We got the orientation right, So it occurs at roughly 45 to 60. It is still recording. Hooray! But it's going to start. Okay, so where do at the shoulder bands, right? Because that's actually where the load shedding gives you a slight stress rise from there. In the physical sample. And so
initiation of
you're right. It has everything to do with the shape of the curve. Yeah, but so let me. Basically, you'll get one here, and often you'll get one here, going at an opposite direction, and they'll move towards each other. Or you could just get one, right? But so you have a shear slip band that forms a distinct region between an undeformed and a deformed region. And you know, sorry, my allergies are killing me today. What's the atomistic mechanism that leads to that softening? Why it's so much harder to initially yield? There's a term. We didn't cover it because it's one of these. It's only applicable really to like metals people. It's a control. It's dynamic strain aging.
Yeah.
So you have interstitials that your dislocations interact with, but at the same time you also have solute chemical segregation around the defects, and they're dragged along. So that's why it's harder to initially yield, because your dislocation is interacting with all these super defects, you can say, almost, right? And then once it's through, it's moving faster. The dislocation is moving faster than the diffusion can occur. And so you break away from this Cottrell atmosphere around your defects. Okay, so now let's pretend this is a polymer sample. Right? So we'll keep this on here. But where in general is that going to start? Is there any preferential spot on your sample for the drawing to occur to begin?
The gauge length.
Yeah, somewhere in the gauge length, right? But it's not necessarily at the shoulder. And what's the orientation relative to the sample of your drawn region? What's that?
Parallel to the tensile axis.
Not parallel, but the line is, right, so your drawn region looks like
It's going to elongate.
right, it's going to elongate, so you get your interface between the deformed and undeformed region is perpendicular to the tensile axis.
You meant, like, how's it going to shorten?
Yeah. No. I get what you're saying. So those are the main. There's a lot of similarities and differences, right? So cool. Okay. Thank you. So the next group.
Why that opposite side of that opposite orientation occurs?
It's actually a testing phenomena because you're never perfectly aligned, so you actually get a slight bending moment. Right? If you had a perfect test, there'd be no preferential orientation. But since you can never be perfectly aligned, your sample has a slight bending moment to it, and that's what will give you that.
So in perfect testing, the nodal bands won't form in the middle. It should form in the top part.
The Luder's band will almost always form at the shoulder because you have a slight stress riser there because of the load shedding.
But if it was perfect, then it would form anywhere.
If it was perfect, it would form anywhere, right? If you had a infinitely long, perfectly cylindrical test specimen, right, and you pulled it perfectly straight, there would be some defect in that length that would cause it to form there rather than at the. It's just.
It needs a nucleation spot.
Yeah, mechanical testing is never perfect.
Yeah.
Right. And ideally, even if we had a perfect test specimen that was perfectly machined with no surface defects from our machining operation, and we were able to pull it perfectly straight, I don't think there would be no preference to form at the shoulder either. Right? Just the fact that nothing is perfect. Yeah.
Say maybe a stupid question. Just looking at two correct orientation, like that in that orientation.
Yeah.
Does that mean it's disoriented like that, or like this, or what does that mean?
So it's just you've got a slip band going this way and a slip band going this way, right? So you have two directions of maximal shear, right? Both oriented at 45 degrees to your sample. It's just now you can imagine if your sample is slightly crooked and you're pulling it, so now you have a bending moment. You're going to have a slightly higher stress on one of those two choices than on the other, and because if it's slightly bending, they're going to be opposite, like this, right? So it's just a slip band that's propagating.
So from this drawing, so the right side where the Luder's band is right on the shoulder, that's probably the side that gets
Yeah.
stressed.
So if you go to the Wikipedia page, there's a finite element simulation. Is it finite element or is it? Let me look it up.
It's actually a
DIC. It's digit image correlation, right? And what you see actually is it starts like this, and then as they get closer together, one of them actually rotates and changes direction, so they come together parallel. What? No. But yeah, so if you go to the Wikipedia pages, the image is there. Right. Okay, so let's go on. So the next question.
Okay.
Okay,
So I'm going to work on question 8.19. And the first part is we want to get the criterion approximate expression for Kray's yielding. And if we look at equation 8.15, we get the equation like the sigma maximum minus sigma minimum equals a constant that depends on temperature plus another constant over the hydrostatic pressure. So for this part, what we only have to do is plug in the equation and get the constants. So from the problem, we get two criteria. The first one is we have a uniaxial tension, which means like if I set the one direction to have the tension of 22 megapascal, then the other two directions are 0. And this is the uniaxial tension that the Kray's yielding started. So in this case, the sigma maximum will be sigma 1, and the sigma minimum will be 0, like either of them. And for the second case, we have a biaxial tension, and we have sigma 1 equals sigma 2 equals 20 megapascal. And this also means sigma 3 should be 0. And in this case, we still have sigma maximum, which is 20 megapascal, and sigma minimum should be 0. So if we plug in these two equations, and then we can get the constants to be approximately 17.53, and the other one to be 32.79. And both of the criterions are at room temperature, so we can get the constants. And for the second part, we'll have to compare it with the band sharing criterion. That was an example in 8.1. So this is the first part.
Okay, so before we hop on, what if you had a biaxial state that was mixed, right? One direction was tension, one was compression.
Then
Right, so say this was now sigma 1 equals 20 and sigma 2 equals minus 20.
oh, because we're only considering like 2 tensions, and the third direction should still be 0, but the maximum is still positive 20, and the minimum will be negative 20.
Yeah, so it's not, when it's max and min here, this isn't the absolute value, right? It's the actual, you need the signed value, right? So a compressive load is more negative than 0, right? So a lot of people make that mistake, that's why.
Why? In the sense of just not numerically.
Just numerically, they say, oh, well, 0 is smaller than 5, right? Even though it's minus 5. All right. So, okay. I just wanted to make that point because it's one that I saw a lot on the exam last year.
Okay. So for the second part, we're going to compare with shear banding and see which of the yield criterion will start first. So what I did is I didn't double check the values I got, so I might be wrong here, but what I got is because sigma 3 is 0, so we can only plot sigma 1 and sigma 2 in the 2D plane. So for the shear banding criteria, I got something like a weird, anyway, I'm not good at this. So if I got a circle, this means like the criterion, if I have stress higher than this, I will start shear banding. And for the crazing criterion, I get something like this. Well, anyway, so in this case, if I have higher loads, then I will start crazing for the crazing criterion, which are the 2 lines I was drawing. So, for example, if I have sigma 2 load that is higher than this value, then I'll start crazing instead of shear banding. So you can examine the criteria after you get the values and try to draw the graph like this.
Okay. So, no, that's fine. So, for your own benefit,
Okay.
right? for the not just for you, it's for the whole class. Right? There's a couple really important points on this graph. Right? First, you need to know where your yield surface for both intersects the axes. Right? You're also going to want to know the intersection points between the crazing and the shear banding yield surfaces, right? And make sure you understand the effect of pressure on each, right? Why you should know that, I'll leave it up to you. Okay, so last one. Yeah.
Let me ask a question about are we going to cover notes?
Yeah, but go ahead. If you have a question, ask it now. Right? That's the point of.
How do they derive the shielding curve? I mean,
That's a completely empirical relationship.
it's just completely empirical.
Yeah, basically, if you look at the figures in the note, they just did a bunch of experiments
Yeah, they're all.
and looked at where the boundary was between not observing and observing, and tried to fit a form for an equation that fit through there.
Okay.
There's no right. When I say there's no physics, right, it's an empirical relationship, right? So F equals ma is an empirical relationship,
Yeah.
right? So there is clearly physics in it's a rule, but there's no mechanism for behind this
I guess it's
behind this form. Yeah, there's not a mechanistic dependence. The shear banding yielding on the other hand comes from J2 plasticity theory. J meaning the invariance of the deviatoric tensor rather than I, the invariance of the full tensor. Right? So it comes from the second invariance of the deviatoric stress tensor. And there is a lot of physics there, but it's definitely not within the scope of the class because it's continuum plasticity theory. Right? So it's not, again, it's not mechanistic. Right? It has to do with a lot more with fundamental continuum mechanics. And I would cover that in the plasticity course if that ever gets on.
This equation looks like Tresca criteria. This one. Similar.
Yeah, well, Tresca gives you, it's similar, except this is nonlinear. Tresca gives you straight sides, right, because it's just the principal stresses, right? So there's a whole bunch of different yield theories, right? What Supriyo was saying is there's another popular yield criterion, Tresca, and what it does is it gives you a linear sides, right? And it works well for the brittle materials like ceramics and things like that. It's mostly, whereas von Mises is ductile failure. Okay, so we've got one last question, right? Okay, nice. The brave volunteer.
Three of us.
And he's coming up without notes too.
Yeah, why is not present here? Okay, so I don't have the problem on me, but if I remember correctly, the problem was asking was given this is a relaxation modulus over log of time. So in the text, so there's a plot given relaxation modulus with respect to temperature. They was saying that when the elastic strain is dominant over plastic strain is, but this time we just need to think it in the with respect to time. So the plots are given in the text, looking like that. So this one on top, it's indicating the relaxation modulus changes of the crystalline material. And this one bottom is non-crystalline or amorphous. So, well, this is more of a like conceptual problem. So I may be wrong, but you know, if I think the crystalline material is more acting like metals, just because it's the crystalline lattice structure nature. But the amorphous material, we need to think when the elastic nature is more dominant over plastic. And so the question is asking, the problem is asking the strain changes over log of time. So I think, since the relaxation modulus in the beginning is similar, let's say it starts over here, and then the crystalline material goes like that, and the amorphous material will go like this, maybe. So,
Okay.
so when the elastic modulus is more dominant, it's going like that, and it goes through the phase change transition to the where the plastic strain is more dominant, and goes. I was just following this the modulus changes.
Okay, so let's think about this in a slightly different way. Okay, so how does a crystalline material respond, an ideal crystalline material, we'll say, respond to an instantaneous load? Right, it's elastic, and it's what shape is the curve? Linear.
Yeah.
Right, so you have a step there, right, that corresponds to, so you just kind of want to pop it back to, yeah, well, both of them, right? Right? You've got, what was there? No, here. So this, right? And now if this was an ideal elastic at a constant modulus, what would this curve look like? Right? If the relaxation modulus was a constant, right, meaning there is no time dependence of the modulus, right? What would the strain curve look like if I put a load on it and just held it?
Well, if it was metal, it should stay constant.
It would just stay constant, right?
Yep.
But in reality, it doesn't, right? You have the modulus is slightly decreasing, so that means the strain is going to slightly increase, right? Which you have.
Mm-hmm.
Okay.
Yep.
So does that give you more confidence or less confidence in what you put down?
Oh, but I'm not. Still not confident with this amorphous material. That
Okay,
goes
so
through
what does the let's ask the peanut gallery. What do you guys think?
So when the modulus sort of jumps down, not only should really the slope of the thing should increase, right?
Mm-hmm.
Rather than just kind of being up in the air with the modulus curve, it should steepen rather than jump.
Yeah. Right. So the modulus is the slope of the strain curve. Right. So when your modulus goes down, your slope
So,
goes up.
so just looking at this modulus change, I think I can intuitively just draw this as well as this as well. But I don't fully understand the atomistic kind of analysis on like why this transition happens, like between elastic and plastic regions. Would you help me understand that?
I'm not sure I understand the question.
Well, in the first place, why does this transition between plastic and elastic happens over and like kind of repeated?
Well, this here, right? I mean, this is just this is experimentally measured, right? What's actually going on in that sample? I don't know. Right? Why are we causing those steps? Right? It's going to be you're activating different mechanisms, right? So even if you just think about a cross-linked polymer with no crystalline regions, right? When we talked about rubber elasticity, we talked about how the basic simple theory breaks down because not all cross-links are cross-links, right? Right. You also have all kinds of other chain interactions, and the kinetics of those interactions behave at very different scales. So to actually say what's happening in there, I'd have to give you some bullshit answer there. Right? Maybe some of the people in here that study soft materials would be able to. But there's going to be a mechanism change of deformation, right? That's the only thing that can really account for changes in the curve like that. But what exactly those specific mechanism changes are, I can say that it's going to have, if I was back on my candidacy exam, right, and this was the question posed to me, I'd first start by saying, I don't know exactly, but here's what I think, right, and it would be the mechanisms, right, and then I'd probably be told I was wrong, right? But so that's I'll say that my wise words of the day, right, is for those of you who have not had your candidacy exam yet, if you keep talking, your examiners will help you. If you stop talking, there's nothing we can do. Right? So the best thing you can do with a question is be honest and say, I don't know, but let me think about it out loud. Right? And put something down. And either two things will happen. Either you'll be sort of on the right track and we'll guide you, or we'll get really frustrated because you're going off into left field and be like, no, come back, start here. Right? But if you stand at the board like a deer in the headlights with a pen in your hand, there's not a damn thing we can do to help you. So that's why I think oral exams, that's why I was hoping you guys would do an oral exam, because it gives me a lot more opportunity to not train, but like pick at what you know instead of giving you one chance to throw things down. Well, there was so much opposition to it, right? It's a syllabus change, so it needs unanimous class approval. So there won't be an oral exam. Yeah?
Just a question. So if you want to have an oral exam, how would you grade it? Like, how would you do that to grade it?
Do you sound like
What do you want to do? Like,
Well, I mean, it wouldn't be pass or fail. It would be like, I think, it would be, there's a minimum standard of what I think you should know for this class, right? And that would be a C, right? I don't think anyone is in danger of getting below that, right? I think, right? And then A to B is how much above that minimum you demonstrate. So Maybe I'll make a option if someone wants to do an oral exam, they can. If not, they'll take the traditional final. So, okay, I want to hit just the main points from the lecture. Let me pull up the notes so I don't miss anything. Oh, Gorsuch was just sworn in. They changed like single sign-on, changed me over to single sign-on, and now it takes forever for my password to register. Okay. Okay, so what are the big things, right? And by big things, I mean the key concepts that you're likely to be asked about, right? Because this is what so really the biggie, free volume, right? What the heck do I mean by free volume, right? What is free volume? Right, so this is, honestly, I've talked about my toolkit, right? My material science problem solving toolkit, right? The Hume-Rothery rules, square root dt, right? The Arrhenius law, right? The Schmidt factors, right? The basic things. For anything that's not metals, like free volume is my starting point. Because it has to do, it's everything, right? If you know nothing about polymers, start with Flory, right? You probably saw Flory-Huggins and thermodynamics, right? The extension of regular solution theory for long, right? And all that work started from this concept of free volume, right? So if you think about polymers, right, it's the amount of space in your sample that the chains have to move above and beyond. There's the space, what they would have in an ideally packed material. What the heck do you mean by ideally packed, right? That could be a crystal, right, if it's a metal, right? Or it could be a maximally packed amorphous, right? And different people take different things as to what you mean by the reference state. But the idea is greater free volume. Anything involving deformation or diffusion is going to happen a lot faster because you've got more room for things to happen. There's significantly, in a packed train, there is significantly more free volume about the guy that smells really bad, right, than about someone else, right? It applies to all kinds of situations, right? So it's just a really useful way of thinking about the world, right? And so it makes sense, right? If I have right, viscosity, right? So viscous flow, where stress is some function of the strain rate, right? This is just kind of the basic viscous flow rule. Right, it makes sense that this viscosity is going to be a function of a bunch of things, right? The biggest one being the free volume, right? If it's Newtonian, right? But also be a function of temperature and strain rate, right? Right, it makes sense. I increase, how does the free volume depend on temperature? Right, as temperature increases, free volume increases, right? Strain rate is a matter of how fast things can get out of the way, right? And it's much more complicated than it is in metals because it's amorphous materials tend to be Newtonian, right? polymers tend to be shear thinning, right? Whereas thick emulsions tend to be shear thickening, right? You just have frictional forces between, mud, right? I mean, who doesn't like playing in mud? It's just basically you get frictional interaction between all the little silt particles, right? You have shear thickening behavior. So understanding, thinking about how viscosity is going to be affected by the free volume, right? The reaction rate rules and the free volume viscosity, right? These things break down as temperature approaches the glass transition temperature, right? To get into what's happening in that regime, you need to do some consideration of transition state theory, right? And some atomistic stuff, which is talk to someone in Wendell's group, right? But well, I mean, David Rigner and yeah, but his thesis had a discussion of transition theory, transition state theory, and viscosity that even I could understand. So talk to David. Okay, so the other key idea I think that's important is these Ashby deformation maps, right? Basically, this is going to be the log of the stress normalized by the shear modulus, right? And this here is temperature, right? And so if you think about what happens, this is the, let's say this is the glass transition. This is not a good drawing. Okay, so down here, these are very low stresses, right? Up here, these are higher stresses. And down here, you have this like linear elastic region, right? You've got a viscoelastic region, right, as I raise the temperature. But these are still under very, very low stresses. If I raise the stresses, I'm suddenly into, over here I have melt, right? Viscous, pure viscous flow. Up here, this whole region, it's inhomogeneous, right? Where shear banding and crazing are much easier to operate than homogeneous flow, right? Almost in glasses and in metallic glasses, you're always in this regime, right? You have to load something so under such small stresses to access this regime down here, right? So any load that's reasonably going to be applied to these materials are up in the homogeneous, right? So why is this inhomogeneity naturally come out? Right? Well, what did we say? You've got viscosity as a function of strain rate, temperature, and free volume, right? And so what's going to happen, right? I've got a glass, it's not perfectly uniform, right? I've got fluctuation, a free volume fluctuation throughout my material. I load it, which means now I don't have a uniform. Let's just even assume I have a uniform stress state. We'll keep it simple. If I have a uniform stress state, but a locally varying free volume composition, I'm going to have a locally varying viscosity. Right? So I'm going to yield at some place first. When I yield, what happens to the material at that point? It gets flowing, but what happens to the strength? It gets softer, which means my stress in it can't support nearly as much stress now. So the stress in the neighboring region becomes higher because you have load shedding, which means that region now starts to yield. Right? And then once I have a significant region that's flowing, I also have the energy dissipated in that, which goes into heat, which makes that whole region softer. So it's a self-accelerating system. Once I get plastic flow in the glass, right? And I'm not talking, and we're not even talking about. I'll get that in a second. But once you start, you have a runaway system. Right? It's a self-accelerating system, and it's going to immediately propagate from one side of the sample to the other. Right? Unless you put something in there to block it. It's basically the same thing that happens with fracture in organic glasses, right? You don't have any appreciable plastic flow, right? But you've got a huge store up of strain energy. Once you nucleate a crack, right, your system gives off a heck of a lot more energy by opening up the crack than by doing anything else, right? So it just zips along. The shear band acts the same way, right? You dissipate a huge amount of elastic strain energy by forming a shear band, right? We talked about drawing, we talked about the yield surfaces, we talked about crazing, we talked about the effective pressure, right? And it's really kind of self-intuitive, right? If I have hydrostatic compression, right? If I have a positive or negative pressure or negative hydrostatic, it's weird. We talk about pressure being opposite in terms of the stress, right? So if we have a negative hydrostatic stress state, it's harder to open up cracks, right? So crazing has a huge change in its dependency based on the hydrostatic pressure, right? Right, and obviously if I have a biaxial state, if I have a dilatational state, it's a lot easier, right? Shear banding has a pressure dependence, but it's less, right? Because you're interested in the difference between the maximum and the minimum, right? And so you can think about how affecting that, what adding numbers to that trace does, right? So conceptually think about it, but it's pretty, and those are the main points that I really want you to remember, right? So we'll call it a day then.
The modulus that changes when you pull the polymer samples 45 degrees softer.
I'm not sure I understand.
When you the pulling the direction you are pulling,
Yeah.
elastic modulus increases, and also the perpendicular direction modulus increases. 45
Oh yeah, so the development of anisotropy, right? So this is a kind of a puzzle I want you guys to think about, right? so the question basically is, so at low, right, you get something that goes like this, and then at higher strains, your modulus, right? So initially, if it's isotropic, right, it makes sense that it's roughly random in all directions, right? And then think about the structure along the tensile direction and this, right? So don't get confused by the strength of the bonds. Think about the stiffness of the bonds, right? Because you still have strong chain alignment, right? And you've got different types of bonding in each direction. But think about the relative stiffness of those bonds and the angular dependence of the stiffness of the bonds, right? So how does a pulling against van der Waals forces change as you're changing your direction, right? Right. So just think about it, and if you still have questions, we can go over it. But yeah, but thanks for bringing that up.